You know, behind every single app you use, every website you visit, there's this invisible architecture holding the whole thing together. It's the system that stores and organizes all the data that makes everything work. Today, we're going to pull back that curtain and really explore how that hidden architecture gets built and why getting it right is the secret to making software that's not just powerful, but reliable. We've all been there, right? An app just crashes out of nowhere, your shopping cart mysteriously empties, or even worse, your data just disappears. It's so easy to blame the code, but a lot of the time, the real problem is something much deeper. Just imagine if all of an app's information was just thrown into this chaotic digital junk drawer. It doesn't matter how good the code is, if it's trying to find something in that mess, things are going to go wrong. And here it is. This is our data junk drawer in action. It's a report from a construction company. Now, at first glance, it looks fine, I guess, but look a little closer at that employee info. We've got multiple names, job classes, and hourly rates, all just crammed together into single cells. As a quick report, maybe it works, but as the foundation for a real database, oh, this is a total recipe for disaster. So what kind of chaos does this junk drawer actually cause? Well, for starters, you've got update nightmares. Let's say an employee's hourly rate changes. You have to go on a scavenger hunt and edit every single project they're on. If you miss just one, your data is now inconsistent. Then you've got these risky deletions. What if the last employee working on the Starlight project leaves? If you delete their row, you could accidentally wipe out the entire record of the project itself. And get this, you can't even add a new employee to the system unless you first assign them to a project. These problems have a name. They're called data anomalies, and they are the source of so many bugs. And that really brings us to this critical point. This quote just says it all, doesn't it? You can have the most brilliant programmers on the planet writing the most elegant code imaginable, but if the data structure underneath it all is a mess, the whole application is always going to be fragile and limited. The foundation, it just has to be solid. Okay, so how do we fix this? We start by building a much better structure. We're going to take our junk drawer and turn it into a perfectly organized filing cabinet. And this first big step is called advanced data modeling. It's all about creating a logical blueprint for our data before we even put any data into it. So the first concept we need to get is something called an entity supertype. The best way to think of it is as the main, big drawer in our new filing cabinet. So for our example, we'd have a supertype called employee. This is where we're going to put all the information that is common to every single employee, like their name, employee number, hire date, all that good stuff. Now this slide shows you exactly why this is so important. On the left, you've got the messy way, one giant table for everybody. But what happens when you have specialized roles, like pilots who need a license number? You end up with all these columns that are just empty for most of your employees. It's a waste of space, it's cluttered. But on the right, that's our smarter filing cabinet. The general employee supertype holds the common info, and it connects to these specialized subtypes. You can think of them like folders for pilot or mechanic that only hold information unique to those roles. And just like that, no more empty cells. And the way this works is through a really powerful concept called inheritance. It is so efficient. When we make that pilot subtype, it automatically inherits all the attributes from the employee supertype. So it gets the employee number, the name, all of that, without us having to do it all over again. Then we just add the stuff that's unique only to pilots. It is such a clean and scalable way to model these kinds of relationships. All right, so we've designed our smart filing cabinet. We've got our drawers and our folders all planned out. Now it's time to actually organize the files inside them. This step-by-step tidying process has a name. It's called normalization. Normalization basically happens in stages, or what we call normal forms. We're going to focus on the first three, which honestly you can just think of as simple rules for tidying up. Number one, one piece of data per box. Number two, no partial stories. And number three, no hidden dependencies. Let's break down what each of those actually means. Okay, rule number one. This is the big one, the most fundamental. It's called first normal form, or 1NF for short. And it's super simple. You cannot have repeating groups of data. Every single cell in your table has to contain one and only one piece of information. That's it. So let's go back to our junk drawer. You see the problem right here? This one cell for the Evergreen project has 5 employee numbers, 5 names, and 5 job classes all stuffed inside. That is a classic repeating group, and it totally violates our first rule. So here's the fix. To get our data into 1NF, we just unpack those repeating groups. Now, every single project employee assignment gets its own unique row. See?
We've solved the one piece of data per box problem. But in doing so, we've created a brand new problem, a ton of data redundancy. Just look at how many times Evergreen or John G. News is repeated. That's not just inefficient, it's a breeding ground for typos.
And all that repetition is exactly what Rule 2, or second normal form, is designed to eliminate. The rule says that all the data in a row has to depend on the entire unique identifier for that row, what we call the primary key. In our table, since neither the project number nor the employee number is unique by itself, the key is the combination of both. 2NF says nothing in that row should depend on just one part of that key.
And here's the issue. The project name, Evergreen, only depends on the project number, 15. It has nothing to do with the employee. And likewise, the employee's name and job class only depend on their employee number. These are called partial dependencies, and they are the root cause of all that repeated data.
The solution is to break this one big table into smaller, more focused tables where each one has a single clear subject. So we create a project table just for project info, an employee table just for employee info, and then a third table called assignment. And that third table is the key. It's the glue that just records which employee is assigned to which project. And just like that, each piece of info is stored only once, and all that redundancy is gone. We are so close. Our final tidying rule is third normal form, or 3NF. Now this one's a little more subtle. It's about finding these hidden, indirect dependencies. The rule says that every attribute in the table has to depend directly on the primary key, and not on some other attribute in the table.
So let's take a look at our new employee table. It's got the employee number, their name, their job class, and the charge per hour for that job. But, wait a second, does the charge per hour really describe the employee? Nope, it describes the job class. Every elect engineer has the same charge per hour. So the charge depends on the job class, which in turn depends on the employee ID. That is a transitive dependency, and it's the last piece of clutter we need to clean up. And the fix, you guessed it, is to create another new dedicated table. We make a JOB table that holds just the job class and its charge per hour. The employee table now just points to the right job class. Now, every single table has one and only one purpose, and that is the ultimate goal of normalization.
Okay, so after all of that work, modeling our data, creating supertypes, and marching through those 3 stages of normalization, what did we actually accomplish? Let's look at the payoff, at what a perfectly organized system really gets you.
This is it, our final, beautiful design. Remember, we started with one chaotic table, that digital junk drawer. We now have 4 clean, lean, and laser-focused tables. One for projects, one for employees, one for jobs, and one for assignments that links them all together. This is our perfectly organized filing cabinet. So what does this actually buy you? First, data integrity. Your information is now trustworthy and consistent. Second, it's way more efficient. If a job's pay rate changes, you update it in exactly one spot. Done. Third, flexibility. You can add a new employee or a new project, and it's simple. You're not going to break anything. And finally, you get reliability. All those update, deletion, and insertion anomalies that cause apps to crash, they're gone. So now we've built this perfectly clean, normalized, organized system. But that leads to a really interesting real-world question. Is this perfectly tidy system always the fastest? And maybe surprisingly, the answer is not always. See, while our tidy system is amazing for preventing errors, it can sometimes be a little slower. To get a single report, the database now has to look at 4 different tables and stitch all that information together. So in some really high-performance situations, designers will actually intentionally break a normalization rule to get more speed. It's called denormalization. They might combine a couple of tables back together, sacrificing a little bit of that perfect organization for a big performance boost. And this leaves us with the most important takeaway. Database design is both a strict science with rules, and it's also a practical craft of making smart trade-offs to build systems that don't just look good on paper, but work brilliantly in the real world.